So all three trig substitutions are similar in the sense that all three trig substitutions get rid of the square root. That's what they do. And they might end up making things more complicated in other ways. So they're not, a guaranteed method of solving stuff. But they always, with 100% reliability, will get rid of that square root. And when you do the sign substitution, it's the Pythagorean identity. And it's going to be the Pythagorean identity for the secant and the tangent as well. But it's going to be a variation on the Pythagorean identity. And I don't think you need to necessarily commit these to memory because I haven't. I just rederive them when I need them. But you can get two other statements from this. If you divide both sides of this equation, alternatively by the sine squared and by the cosine squared, because what's going to happen here, when we have addition in the numerator, it's going to break into two. The sine squared over the sine squared. I'm going to just briefly rewrite this. A square divided by a square. So the cosine squared over the sine squared, that can be rewritten as a single square. And we can do the precise same thing on the right if we think of 1 as 1 squared. So the sine squared over the sine squared is 1. One divided by the sine is the cosecant. So if instead of dividing by the sine squared, we divided by the cosine squared, we'd have gotten something that looked nicer in the sense that it involves trig functions we're maybe a little more used to. The cotangent and the cosecant are kind of the castaways of trigonometry. So using the same logic that we used on the previous frame, sine squared over the cosine squared will give us the tangent squared. The cosine squared over the cosine squared will give us 1. 1 divided by the cosine squared will be the secant squared. And when it's not on the whiteboard, anyone listening to this recording, we had some technical issues at the beginning of class and we were using the physical whiteboard. but the substitution we're looking at very briefly is this. And when we do this substitution, we're going to wind up with a secant squared theta, and we'll use the Pythagorean identity to rewrite that as a perfect square. Let's see how this works. And this is a really, I'm going to say it, this is a really delicate process. I mean, it always gets rid of the square root, but it's really a question of whether you'll be able to integrate what you get after you do the U substitution. So these problems are all a bit lab grown, as it were. They're designed to work out nicely. See, and again, we make our life nice in these lab-grown problems by using perfect squares. That's not important. I mean, if we had, instead of a 4, if we had a 7, we could still do this. It's the important thing is that we have subtraction there. If we had addition, it would be something else. It would be a different substitution. But going back to what I put on the board, we see that square root. We should probably at least pause and consider alternatives. I mean, sometimes when you have a square root, that's an indicator that you should try U substitution, but our hopes are dashed here. We don't have a 2x, and we do have an x squared. So U substitution is probably not the way to go here. No, in fact, I'll say it's definitely not the way to go. And we'll try the trig substitution. And whenever you do trig substitution, the next thing you write on the board is going to be much messier looking than what you started with. So we have to just kind of hope that at the end of the day, when we've done all of the simplification and the dust has all cleared, we somehow wind up with something nice. The one guarantee is that we will get rid of the square root. And the dx, often you see dx written up in the denominator of fractions. I don't like doing that myself because the dx is not a number. The dx is not an abstract symbol. I don't love having it in the denominator of fractions as if it were just a number, but out of necessity, because I have no more space on the whiteboard, Let's put that up there. And as I say, this looks horrible. It looks worse, but even looking at it immediately, we might see some hope. I mean, we've got a secant in the top and a secant squared down below. So that ought to simplify. But let's take a look at this square root. 4 times the secant squared minus 4. So the exact same thing is happening here as happened with the sign substitution. The way we do the substitution, the number in front of this trig function and this number here will always be the same. We get the secant squared theta minus 1. And one of these, here we go. Let's see if we just subtract that 1 over to the right, then that thing in the square root becomes a perfect square. It becomes the tangent squared. And again, this is the trig substitution guarantee. Things might get messier in other ways, but it will always turn that thing under the square root into a perfect square and let us get rid of the square root. There's our denominator. Let's see. 2 times the secant squared is 4 times the secant squared. So again, we see some hope here. The secant on the top and the secant down below, some cancellations going to happen. The square root again going to sweep a few technical details under the rug here, just like with the sign. We have a sort of technical issue that really the square root and the square don't cancel each other out. They give you the absolute value. Here, for technical reasons, we can assume that the tangent is positive and the absolute value of the tangent is just the tangent. So we don't let this bother us, at least for the moment. And a whole bunch of simplification occurs now. That's the dream, that we're making things messy looking to start with, but you'll end up with something that we can approach. Now, ordinarily, this something like this would actually be a big problem, like we know how to integrate, or we can integrate the natural log using integration by parts, but we can't integrate 1 divided by the natural log. So ordinarily having a fraction like that would be a bad thing. Here it simplifies in a very quick and pleasing way. How does it simplify?
Does it just become cosine?
It becomes the cosine because the secant is 1 divided by the cosine, and 1 divided by 1 divided by the cosine is the cosine. And now here we pause and think. Of course, theta isn't real. I mean, it sounds a little silly to say that, but theta is like you drew a right triangle and you labeled an angle theta, but we don't want this as our answer, certainly. And with what I have written on this whiteboard, it's not at all obvious how to proceed. Or maybe it is. Let's see if we can. No, it isn't. So, we could take this and, I don't know, x equals 2 divided by the cosine. If we had the cosine of theta on the other frame, that would be just something we could get right from this equation. But we have the sine. And here's where it's helpful to have right triangles in the back of your mind. I know anyone watching this video didn't see this part because it happened on the physical whiteboard, but the picture that's giving us this x equals a times the secant of theta is this picture. Here a is 2. And now the cosine of theta, or sorry, the sine of theta is a piece of cake. We just use right triangle trigonometry. The sine is the opposite over the hypotenuse. The square root of x squared minus 4. Hypotenuse is x. Let me see. Don't write it quite like that. We don't ever have the constant of integration stuck in parentheses. We'll move it outside. But I don't know, sometimes my hand sort of feels like it's just doing stuff at random. So that's a second trig substitution. And in this situation, it worked out perfectly, well, maybe perfectly nicely is overstating things. Trig substitution is always a lot of work. Although I don't know, I have had students tell me let's not overstate things. I've had a student tell me he enjoys this material, so maybe I shouldn't make assumptions. The other trig substitution, you could maybe kind of, if you remember the inverse trig stuff, the x squared plus a squared gave you the inverse tangent. So from that point of view, it's not shocking that this is the substitution we do. The picture that motivates it is this. Again, the way trig substitution sort of works is we've got a square root, but we don't want a square root. Square roots are messy. So we can avoid looking at the square root. We can look at the other two sides of the right triangle, with obviously the trade-off being that now we have trigonometry. If we want to look at those other two sides of the triangle, we need to do so with a trig function. And it's going to be either, well, no, I mean, it has to be the tangent. We want to relate the opposite side over the adjacent side. That's either the tangent or the cotangent. And if we tried to use the cotangent, the same thing would happen over there as when we tried to use the cosine and we ended up with the secant. If we try to use the cotangent, we end up with 1 divided by 1 divided by 1 divided. God, I don't know. Sometimes my mouth just runs away from me, and I have no idea why I'm saying the things I'm saying. So, the tangent of theta is the opposite side over the adjacent side. That's not quite what I want, is it? And I think the solution is simple. I think the solution is that I messed up drawing that right triangle. This is what I was babbling about earlier. If we let x be the if we used this diagram, we'd wind up with the cotangent. And I mean, winding up with the cotangent isn't the end of the world. We would still make it work with that trig identity. But what I think I must want to do here, because I mean, the legs of this right triangle, this right triangle will continue to hold code. If I reverse the legs, that's still correct. And now the opposite side is x and the adjacent side is a. And I get the expected trig substitution. There we go. Sorry about that. The derivative of the tangent is the secant squared. And that's, I don't want to dwell on this just because lectures, I mean, I read somewhere that the ideal lecture is like 15 minutes. That's beyond my ability, but I don't want to drag this out too much. Let's just look at an example where at least the substitution works, and we might not be able to evaluate the result. I don't know, but let's just say we have the square root of x squared plus 1. If we had an x out front, we'd be able to use u substitution, but we don't, so we can't. And trig substitution seems like our only hope. 1 is 1 squared. So x equals 1 times the tangent. Dx equals the secant squared d theta. And there's the result of our substitution. And let's see, the tangent squared plus 1 is the secant squared. We can take this and cast it out. Both of the other trig substitutions rely on the same variation of the Pythagorean identity. Tangent squared plus 1 is the secant squared. Actually, if we hadn't lost not 1 but 2 days to the weather, we'd actually be talk about this one in a bit more depth. Because if they're using the fundamental theorem, if they're doing definite integrals, there are times when we want the absolute value. But for now, we're just sort of hitting the high points. And we'll say that the square root and the square cancel out. And we wind up with the secant cubed theta. And here we sort of here we sort of sit. I'm sure that there's some trick for taking this integral, but I don't know it. And you sort of, there are so many tricks you can learn in calculus too. You have to kind of pick and choose. But we could, if we had a definite integral, we could use any of the rules, trapezoidal, Simpsons, etc. Since we have an indefinite integral, we could see if technology could help us. We could try Wolfram alpha or something like that. At any rate, you see that trig substitution did accomplish what it was supposed to accomplish. It did remove that square root. And I'll end things here. Next week, it's, I think, supposed to get into the 50s, which is hard to believe, but hopefully no more weather emergencies.